In this module, we shall introduce logistic and Probit regression. These are very common popular models used to model binary outcomes, and we shall study these in great detail in this paper. The logistic model arises when we use the Logit link, and the Probit model arises when we use the inverse cumulative normal CDF as the link. Now we know that in theory, any link function which maps onto the desired range, in this case maps the probabilities between 0 and 1, is acceptable. However, from the viewpoint of a practitioner, we need to have some justification for the choice of the link. We can see this from the binary choice model. We know that the binary choice model explains logistic regression and Probit regression from the viewpoint of econometric theory and the utility function, and the distribution assumed for the underlying latent part of the utility will determine the choice of the link. Assuming a logistic regression distribution will lead to the logistic regression model, and assuming a normal distribution will lead to the Probit model. Now, as this latent variable is unobserved, we cannot really use modeling techniques such as scatter plots to determine the choice of link, and this needs to come from substantive conclusions. So, for example, we might decide to model a distribution with low tails in terms of the normal and a distribution with higher tails in terms of the logistic distribution. The logistic model also has one more attractive property, which is that the estimated coefficients can be interpreted as log odds ratios. The Probit model does not lead to coefficients which have ready interpretations, and to interpret the results of fitting a Probit model, we need to look at the corresponding fits and their plots. Nevertheless, both models are very popular in the literature, and in subsequent modules, we shall look at more details at fitting, diagnostics, applications, R code, etc. In this lecture, we shall consider the problem of defining an alternative class of models to the linear probability models called Logit and Probit models. Recall that in an earlier lecture we had considered the problem of fitting linear probability models to the case where we had a binary outcome with the objective of determining a regression framework which would allow us to model a binary outcome in terms of a set of p predictors x1, x2, xp. The linear probability model, if you recall, has three disadvantages which make it undesirable to the statistician. The first is that it can commonly lead to predicted values which lie outside the acceptable range. The second is that when we are modeling a probability, the concept of linearity is not necessarily a desirable one. And the third is that the residuals for such a model are typically heteroscedastic, which means that the estimators which the linear model gives us are no longer the optimum estimators. In this lecture, we will consider Logit and Probit estimation as an alternative to fitting linear probability models. Logit and Probit models are two particular cases of the models given on this slide. Now note that for the linear model, we had specified that expectation of y given x is equal to probability of y equal to 1 given x is equal to x prime beta. When we move to Logit and Probit models, we now specify that probability of y equal to 1 given x is no longer just simply x prime beta, but equal to g of x prime beta, where g is some known function which lies between 0 to 1. Now we see that this immediately does away with two of the problems of the linear probability model. If g is constrained to lie between 0 and 1, we can no longer get predictions which lie outside the range. And if g is not a linear function, then the probability is also not constrained to be linear. The Logit and Probit models are also particular cases of something called single index models. Now recall that we have P predictors x1, x2, xp. To determine how these predictors affect y, we consider a single predictor function which we denote by x prime beta. As this predictor is linear, note that it is linear in the parameters and not necessarily in the covariates. This is called a linear index, and class of models which uses this linear index to measure the effect of x on y are called single index models. This is a very large class, including many common models which you may have heard of, such as LMs, GLMs, GAMs, and so on. Logit and Probit models also belong to this subclass. Now, I have said that g is a known function which is assumed to lie between 0 and 1. The immediate function which comes to mind is a probability function, specifically a cumulative density function. So such a function will be monotonically increasing, and it will tend to 0 as the predictor tends to minus infinity, and will tend to 1 as the predictor tends to infinity. So suppose, for example, we were to say that G was the CDF of the logistic distribution. The model which this leads to now states that probability y equal to 1 given x prime beta is g of x prime beta. Now we know that gx for the logistic distribution is of the form e to the power x by 1 plus e to the power x, means that we now have probability of y equal to 1 given x is equal to e to the power x prime beta by 1 plus e to the power x prime beta. If you have heard of the logistic model before, then we can rephrase this in its better known form as log of probability y equal to 1 given x by probability y equal to 0 given x is equal to x prime beta. This slide shows a plot of the Logit model. Now you can see that the function is somewhat similar to the linear model, but it bypasses some of the difficulties which we mentioned. So it is monotonic as before. It is increasing for most of the range, but at the two extremities it begins to plateau. I have plotted the function here as a function of the linear predictor. So as the linear predictor increases, the function initially increases, but then starts to approach a plateau of 1. And as the linear predictor decreases, the function initially decreases sharply, but then again starts to plateau at the value 0. In mathematical literature, this function is called a sigmoid function. You may have heard of another class of models called Probit models, which also arise commonly in econometrics. In such a case, we assume that G is the standard normal CDF. Making this assumption, we get the Probit model, which states that probability y equal to 1 given x prime beta is equal to capital Phi of x prime beta, where capital Phi is the CDF of the standard normal distribution. Here is a plot of the Probit model. Now the model looks much similar as the logistic model, which is that it is increasing for most of the range. As the linear predictor increases, it begins to approach a plateau at the value 1. As the linear predictor decreases, it begins to approach a plateau at the value 0. The place where it differs from the Logit model is mainly in the extremities, and we will revisit this later when we discuss as to whether we should choose a logistic model or a Probit model in any particular application. So again, the similarities of the Logit and Probit models. The Logit and Probit functions are both increasing. Both functions increase relatively quickly in the central portion and relatively slowly at the extremities, and both functions lie between 0 and 1. So the key to the specification of lying between 0 and 1 comes from the fact that we have constrained the probability to be equal to a CDF, which will necessarily lie between 0 and 1. While this leads to good properties from a mathematical perspective, from a prediction perspective, we also need a subject matter motivation for explaining why we might want to include a CDF to explain this relationship and how in any particular application we would choose the particular CDF. To understand this, we have to define a latent variable framework. Now, the word latent means hidden or unmeasured, something which is not observed. And so the latent variable framework assumes that in addition to the variables which we have observed, which is the response y, binary, and the set of p predictors x1, x2, xp, we now have an additional latent variable typically denoted by y star. Now, y star is not observed, but it is critical to determining the relationship between y and x. So let me first consider this strictly from a mathematical point of view. The assumption is that the event y equal to 1 happens when y star exceeds some threshold, which I can assume without loss of generality is 0. Next, I'm going to assume that y star is a linear function of the covariates plus a random error. So it has one systematic component which is explained by the covariates and one unexplained component which is the random error. Now, going through these calculations, you see that the probability of y equal to 1 is the probability of y star being positive, which is the probability of epsilon being greater than minus x prime beta. Now, if I assume that epsilon has the CDF G and that G is symmetric, it can be shown that this will lead to the model which I had on my earlier slide, which is that probability y equal to 1 given x is equal to g of x prime beta. So the motivation for g comes from the fact that we have assumed that epsilon has the CDF G. Now, what in any particular application is the interpretation of x prime beta, y star, and g? Our assumption is, now let us make it specific to the problem of migrating from East Germany to West Germany, say, that the chance of an individual migrating from East Germany to West Germany depends on some characteristics. Some of these we observe, they're x1, x2, xp, and we can sum up their joint effect using the linear predictor x prime beta. Some individual characteristics we don't observe, and these are contained in the random error epsilon. So we define a net utility of migrating from East Germany to West Germany, which is equal to the sum of the systematic component plus the random component, equal to x prime beta plus epsilon. Now, we do not observe y star. That is, we do not observe this utility directly. What we do observe is whether or not the person actually migrates to West Germany or not. That is, we observe whether or not y star exceeds the threshold 0, or equivalently whether or not the event y equal to 1 or 0 takes place. So consider another example where we want to predict whether or not an individual will buy a luxury car. Now, the chance of buying a luxury car might depend on some observed covariates, his income, say, the city he lives in, his age, but it might also depend on some unobserved covariates, in the sense that two individuals with exactly the same set of covariates may not have the same tendency to buy a luxury car. So, in this case, we can measure the utility as the sum of the random and systematic components as before, and use the binary choice motivation to determine a Logit or a Probit model. So when we assume that E follows a logistic distribution, our assumption leads to what is commonly known as the logistic model, and when we assume that E follows the normal distribution, our assumptions lead to what is called the Probit model. What is the advantage of using such a motivation? Well, I have deviated from what I was doing earlier, which is using the exact linear model methodology to estimate my parameters. So how would I do it in this case? Now, in this case, once I know the probability of y equal to 1 as a function of x prime beta, and observing that the y's are independent Bernoulli variables, I can always write down their joint likelihood. So, if you recall that the likelihood of a Bernoulli variable is probability of success to the power of y into probability of failure to the power 1 minus y, and using the fact that the probability in this case is g of x prime beta, I can write down the likelihood as a function of beta. Now, having written down the likelihood, I no longer need to define an additional set of methodology because I can always fall back on the principle of maximum likelihood estimation. So here is the likelihood, and I can find the score equations and the Hessian. Now, neither the score will be in, or the MLEs will come in a closed form, as for the linear model, and the properties will be harder to study. But the advantage is that having reduced this to a probabilistic framework, I can use a very well-known technique, which is the technique of maximum likelihood estimation. So maximum likelihood estimation will lead to my estimators, and in addition, it will also give me a set of techniques which will allow me to perform inference about these estimators. So the commonly used techniques are Wall's test, the likelihood ratio test, and the score test. Now we come back to the question of determining whether in a particular application we could choose logistic regression or Probit regression. Now note that the distinction refers to what we assume about the distribution of the latent errors E. Now, if you look at the two CDFs side by side, they are much the same. The only difference which we know about the logistic and the Probit distribution is that the normal distribution does not typically have outliers, whereas the logistic distribution is more heavy-tailed. So if we suspect that we are modeling a population where we might have outliers, it would be more common to use the logistic distribution. An additional advantage of the logistic distribution is that the coefficients which we get are more easily interpretable. Now again, this is something which we will revisit in later lectures. For now, we will note that the coefficients betas are actually what are called log odds ratios, which are typically estimates of the strength of association between y and x. So beta equal to 0, for example, says that x and y are not related, and beta positive says that the relationship is in a positive direction, and so on. For a Probit regression, it is quite hard to extract beta from the regression equation to give it a direct interpretation. However, we can still see that beta equal to 0 means that the covariate has no relationship with the outcome. We can formalize this by conducting a likelihood ratio test of the coefficient beta equal to 0. In this last slide, we see some R code for fitting logistic and Probit models to binary data. The function which is commonly used here is the GLM. In earlier lectures, you have learnt about the LM function in R, which is a core function. The GLM is also a core function in R, and if you recall the concept of R objects, the GLM object is very similar to the LM object. In later lectures, we shall consider a case study which will give us a further overview of the GLM object in R. In this module, we have looked at logistic and Probit regression. We have seen some properties of these two regressions, which are very common choices of modeling when we have a discrete outcome. In this case, a binary outcome. Justification for the two models from a substantive point of view can be derived from econometric theory based on the behavior of the underlying utility of the choice. We have also looked briefly at some properties of the two models. The logistic model has one attractive feature in that the estimated coefficients have easy interpretations and immediate interpretations as log odds ratios. The Probit model coefficients do not have any such obvious interpretation, and to interpret the results of a Probit model, we need to look at the plotted fitted values. These are two very important choices of GLMs which we shall introduce in later modules, and we shall study applications, fates, diagnostics for both models in subsequent modules. The Probit model, however, does have one attractive feature over the logistic regression, and that is that because of the properties of the normal distribution, it is easy to generalize from the normal to the multivariate normal, and hence in the case when the outcome is not binary but has several categories, it is easy to generalize the idea of Probit regression to this multivariate setting.